BalaGAN, Cross-Modal Image Translation between Imbalanced Domains. State-of-the-art, unsupervised image-to-image translation methods struggle to achieve high-quality results when trained on imbalanced datasets. In this example, we see images that were generated by CycleGAN that were trained on 10,000 source domain images and a decreasing number of target domain images, from 1,000 down to 125. The quality of the images drops as we decrease the size of the target domain. Here, BalaGAN translates a dog to a cat based on a reference image. We train the network on 5,000 dog images and a decreasing number of cat images from a full domain of 5,000 cats down to 125, leading to more and more imbalanced domain pairs. The quality of the translated images remains high even when the two domains are highly imbalanced. We present a novel approach specifically designed for the imbalanced image-to-image translation problem. Our method receives an image from the source domain and a reference image from the target domain. It generates a new image which resembles the source image pixel-wise but shares the same style as the reference image. These images were generated by BalaGAN. The structure of the face is preserved in each column, and the style of the wolf is preserved in each row. Our key idea is not to look at the source domain as one piece, but to decompose it into multiple modes. Then we get a multitude of image-to-image translation problems. We train our network to perform translations between all pairs of modes. The power of our method stems from the fact that a single network is trained to perform relevant translations between a multitude of pairs. As a result, the network can perform the translation task better, and in particular, translates between the desired source and the desired target domain better. To split the source domain into modes, we train an encoder and cluster the images by their representations. To train the encoder, we apply 2 random augmentations on each image. Then, we pass the augmented images through the encoder to get a latent representation. We apply a contrastive loss on the representations, decreasing the distance between the representations of the same source image and increasing the distance between different sources. This training procedure encourages the encoder to yield representations which are agnostic to the augmentations. For example, the representation of each of these dogs is similar, even for different lighting, blurring, and flipping conditions. Clustering the representations yields meaningful modes, as can be seen in this image. The translation network is trained to translate between all pairs of modes. It is trained adversarially and consists of a generator and a discriminator. The generator receives an image from a source mode and a reference image from a reference mode. It then generates an image that has the same mode as the reference image. The generator consists of 2 encoders and a decoder. Since we are interested in an accurate translation, and not only realistic images, the discriminator predicts the mode for each image. The generator aims at confusing the discriminator, making it think that the generated image belongs to the reference mode. For a generated image, the discriminator aims to predict any mode except for the reference. This is a rather weak requirement from the discriminator. Therefore, we add another head to the discriminator, which performs classification between all the modes, but is trained on real images only, and thus has to predict the right mode all the time. Therefore, the learned features in the common layers are meaningful and boost the discriminator. As the discriminator becomes stronger, the generator needs to work harder to fool it, and therefore the generated images that we get are better. We perform extensive experiments and ablation studies which can be found in the paper and in the supplementary material. Thank you!